So much for coming. Welcome to the last mile in AI. 2025 has been a great year to build an AI product. Compute has never been cheaper, training extremely cheap, and now we have MCP and Cursor to make POCs on Twitter incredibly easy. I'm very excited about this, but the truth is that getting things running in production is still incredibly difficult. The good news is that us, as engineers, will still be gainfully employed for many, many years because of some of the problems we're going to discuss tonight. And so tonight we're going to have 3 speakers addressing what goes wrong or what is difficult about getting something running online and in production. To kick things off, I'm going to invite my co-founder and good friend, Sam Farid, coming all the way from Pack Heights, to talk about getting agents to work reliably with code. Please put your hands together for Sam Farid.
Thank you, Tim. Nice, okay. All right, hi everyone. I'm going to be talking about how to teach AI agents to make extremely precise code changes in very large GitHub repos. Can you guys hear me okay? Does this sound good? Awesome. Quick background on me. My name is Sam Farid. I'm one of the co-founders of Flightcrew. Flightcrew is a tool that cleans up cloud infrastructure issues via PRs, kind of like a Dependabot. And we work with small and large companies to optimize Kubernetes, refactor their configs and infrastructure as code, and automate compliance and security issues. So using a Flightcrew example to illustrate this concept, we get an alert here. Here we have a container that is failing because it ran out of memory. And so our service is down. What are we going to do? So who should fix this issue? Not me. I don't really want to. This is annoying. It could take a while to look through weeks of metrics and config data. I know that I own the container, but isn't this really the job for an SRE? Well, not really. They have hundreds of other alerts on different clusters to deal with that are higher priority, and they don't know how I set up my config, so it's not really fair to hand this off to someone. So this is a perfect problem for an AI agent. Can an AI agent solve this problem? Yes, it's very hard, but let's talk about it and build it together. So why is this so hard? We are a GitHub app. We have access to the GitHub API. We should just be able to find the config file. We just need to find the right config file to change. So this is kind of like a Where's Waldo problem. Computers are better at Where's Waldo than we are, so this shouldn't be too hard. Except it's more like where's the third red stripe on Waldo's sweater type of problem. We need to find one specific field in that config file to change. We're just looking to change the memory. And so, right, we have this Where's Waldo picture. We need to search a few hundred config files in a GitHub repo. Except config files these days aren't actually that simple. There are a lot of ways that it can be modularized. You don't have raw YAML anymore. In Helm, for example, you have templates and override files. So this is more like if you split up this image into a jigsaw puzzle, and you can't just find the piece that has the red stripe on the sweater. You kind of need to find all of Waldo to make sure it's a sweater attached to him. We all know about those tricky evil twins Waldo has. So, okay, so we need to make sure we include the template files. But actually, this is not really just the case because Waldo does have those evil twins. We are running our same container on many, many different environments, and we need to make sure we're only touching the one environment where this is failing, otherwise we could cause other issues. Okay, so Waldo has evil twins, whatever. Well, this isn't really the entire problem, though, because config languages have something written in code and something else deployed on the cluster. So this is more like you get a police sketch of Waldo, and then you have to find out, based on some of these distinguished features, what does it actually look like in code. You know, if an AI agent is reading from Kubernetes, it gets in JSON. If it's configured in code, it might be in Go and YAML. And so speaking of config languages, you can deploy things from Go or Python. That means we're not just looking through config files. We're actually looking through hundreds of thousands of files, an entire GitHub repo, because you don't know which of the programming files could have a config in it. Okay, fine. So we also have an issue where sometimes there's no source file at all. You can deploy containers from third-party Helm charts. So Waldo continues to drown, and you have 30 seconds to do this. So this is a problem that's hard because it's too complex to solve with code alone, but it's too big to fit in an LM context window. All right, so to keep this analogy going, how would you find Waldo in this imagery of 100 jigsaw boxes all dumped in the same place? Would you try to look through and find the pieces that have the exact red color that you're looking for, and then find the pieces that fit into that? Would you find all the pieces with people in them, and then put those together and discard the ones you don't care about? Would you hire an intern, shove them in a room for 5 days, have them solve the entire puzzle, and then show you where Waldo is? Point of this is just to kind of illustrate the variety of strategies you can take when you're working with a sometimes human-like LLM. But getting back to the kind of real agent that we're trying to build, we have a container that's failing due to out of memory. We want the AI agent to send a pull request, which updates the config to make this alert go away. To be able to judge the quality or success of that agent, we have a few different dimensions. So we're going to be looking at the precision, the recall, and the speed. Precision basically means when we do make a PR, when the agent makes a PR, the alert actually is solved and goes away. The memory issue gets fixed. Recall means of all the alerts, how many of them are we actually solving? And so high precision means you're solving a lot of problems. Low precision means you might be making changes in the wrong place or making things even worse. And low recall just means you're not that useful. And these obviously are kind of, they're not even interdependent. So you can have high precision, low recall. That means you're really good at solving a few problems. You can have low precision, high recall. You're really bad at solving a lot of problems. And speed is, I think, relatively self-explanatory, kind of how fast would it be to get this thing up and running and trained so that it's successful. All right, so let's try some strategies. Let's build this AI agent. First idea, hey, if I'm a person doing this, probably what I would do, I would go to GitHub code search. I would look for some distinguished features of this police sketch or of this config that we're looking for. And crawl the file directory, see if I can find the template files, what's getting referenced, how do we piece this together, and then I would make the config change. So what if we just gave our agent access to the same search API and said, go, good luck? This does not work well. The problem here is you as a human, you're making so many nuanced micro decisions and you're kind of thinking at a really high level that an agent just isn't trained to do. And it's really ineffective, especially when we're searching for specific strings. It's just not something that the agent can make use of. So first learning here, AI agents can't use the same tools we use. You can't expect them to operate the way that a human would. All right, so we know we can solve this problem with a really, really small context window. If we had a GitHub repo that was only 10 files, then that fits in the context window. An agent could just look at all of them, see how they're linked, and find the config we're looking for. So let's try that from a larger scale. I'm going to narrow down writing some code to 1% of the total files, tell the agent, hey, look for this police sketch, find the most Waldo-looking guy, and then make a config change. This does not work either at all. The problem is, as you can maybe tell from the slide, whatever code I wrote to narrow it down to 1%, the actual files that we need are often in that other 99%. And so you can't depend on your code to narrow it down to a smaller scale. Complexity scales exponentially. Essentially, if something works at a small scale, it doesn't mean you can just scale it up and it'll eventually work. It might just take longer. You have to completely restructure the problem. Okay, so I know that my human intuition can work on one single problem. So let me try to explain to the LM how I did it one time. Okay, so I took this police sketch and I found these 3 pieces. Here's an example you should look for. And then based on that, take these other police sketches and see what you can do. We're starting to get a bit better on this one. The precision and recall are going up a bit. What's really incredible about LMs is how remarkable they are at extrapolating from a small amount of ground truth and learning patterns from that. So a little ground truth goes a long way. It's just obviously as opposed to traditional ML systems, which need tons and tons of training data and training sets, validation sets, test sets. You really only need a couple examples and it can tell, okay, I'm looking for this type of sweater. Sounds good. All right, so if putting in a little bit of ground truth works, what if we take that to extreme and use a ton of ground truth? So I'm going to manually look through the repo. I'm going to find every possible corner case that there is, and then use AI to help me write custom functions and parse the config structures. This is akin to let's solve the entire puzzle before we do the search. This is getting a bit better. So we extrapolated on top of the ground truth and our precision recall are going up again. The problem is this is so slow and hard, and anytime someone changes a config structure, your parsers break. This is really not a scalable solution to build a product around. We're getting slower and slower each time. So the insight here, make sure you're offloading any non-deterministic ambiguity. If there's something where a human can mess with your logic, an LLM should be solving that. Do not try to code that yourself. All right, so taking everything that we've learned, let's try splitting the difference and coming up with a hybrid approach. So I can write code that does approximate similarity matching. I can find pieces that look like they have heads and sweaters and pants. And then I can ask the AI, hey, can you disambiguate some of these? Find the police sketch in this limited group based on the clustering. And this is now looking pretty good. So this is a solution we can work with. Essentially, the insight here is that the similarity clustering is pretty good on its own, but there are too many ways that humans can mess with that. And so you ask the LLM to take it across the finish line. And neither of these things would be able to do it by themselves, but they work together. So really, all these insights, AI agents can't use the same tools we can use. Complexity scales exponentially. A little ground truth goes a long way. And offload non-deterministic ambiguity. They really all add up to make sure that you are restructuring the problem to play to the respective strengths of code versus LLMs. The best approach is probably going to be a hybrid approach that looks bad with their individual components, but together they actually become more effective and faster. Thank you so much for listening. This is my contact info. Happy to take any questions. Do we have time for questions? Happy to take some questions. Yeah.
That final slide, that insight around understanding where,
Yep.
Understanding sort of how the strengths play together. Like, do you think of any other problems where this is sort of key to getting to the actual solution? Because this strikes me as like at the core of like the era we're in today. Like companies are trying to figure out like where's that balance.
Right, and the question is what other problems could this apply to?
Another example where this kind of maps.
Oh, yeah. I mean, I think so, right. The example that we're talking about is a very, very Flightcrew specific example because that's what we're comfortable with. But I think what's useful about AI agents is they are unlocking the ability to scale programs where traditional coding wouldn't work at all. And so any time that you're interacting with humans, I think this is humans can inject an amount of randomness that makes this really hard. So I think, for example, I don't know, like customer service chatbots is another example of trying to parse between, okay, what is the API that we need to call and what information do we need to give the customer is a coding problem, but an LLM problem is how do we understand the intent of the user. And so we're doing something similar to that with our Copilot app where you can ask a question that sounds similar to something, but you have no way of parsing that intent with just code. Does that make sense?
Yeah, I'm curious how you tested it. So, like you said, with the Copilot, you have tasks, and then you might have different measures of what like code looks like. How you test it?
Oh, yeah, I love this question. So we are testing internally and externally. and all of the outputs end up feeding back into our input. So, this started as kind of an auto merge internally, and whenever stuff looked wrong, we as humans would catch that and feed that back into the model, and eventually you're learning more and more about the repo and about the training data that you need to provide. So in practice, as we are running these agents with clients or users, they are not putting these on auto merge. There's always a human reviewer, which is the benefit of being read-only. And so if we see PRs get closed, we can feed that back into the model. If we see them get accepted, our precision goes up, our recall goes up. Yeah. Okay. Any more? All right. Thanks so much. Pass us on to the next one.
Thank you, Sam. That was an excellent talk. Now I'd like to welcome Jared from Keycard Labs. Please give him a hand.
Can we mirror that there? Okay. All right, perfect. All right, I'm going to talk about how we can secure agents using OAuth. Real quickly, I'm the co-founder of Keycard, where we're building AI native identity and access infrastructure. For any of the Node developers in the audience, I'm also the author of Passport.js, and I was previously at Auth0, where I built out a lot of their early identity infrastructure, and then have spent the past 10 years prior to Keycard between Auth0 and Okta. All right, we're all super excited about LLMs, and like the fact that they can now call tools and using MCP makes them super useful. Agents that are more connected are more useful. So what's the conclusion here is like, let's connect them to more systems, obviously. But today we face a somewhat impossible choice, which is we can give the agents broad access and accept the security risks, or we can limit their capabilities and sacrifice the value they provide. And this is exemplified by what you see in typical MCP configurations today, which is you go get API keys and you copy them into configuration files and environment variables. If we're to deploy tens or hundreds of agents with this sort of configuration, we've got a real security nightmare on our hands. So what do we do about this? Well, luckily, we know how to eliminate static secrets and replace them with dynamic access using OAuth. So that's what we're going to discuss. All right, so real quick, who's familiar with OAuth in the audience? Yeah, a few people? All right, cool. Well, just to set it up briefly, I won't lie to everyone, like OAuth is a fairly complex protocol, especially if you get into all the sort of like nooks and crannies of it. But at its core, it's relatively simple. It's basically a protocol for applications, which we call clients in OAuth, to request access to APIs, which we call resource servers. And this access is mediated by an authorization server. And if you've ever done anything like connect Calendly to your Google Calendar, you've gone through an OAuth flow, whether you knew it or not. And what's going on there basically is Calendly sends an authorization request over to Google saying, hey, I would like access to the user's calendar. That's when Google steps in and shows a consent prompt, which is very blurry on the screen, but it says, do you want to allow this to happen? Assuming you click allow, then Google sends what's known as an access token over to Calendly, which Calendly can use to access the API on your behalf. There's a few other things going on there, like refresh tokens, but that's the core of it. There's three roles in OAuth which are kind of important to understand. The two, like client and resource server, are fairly easy to understand. They're follow our typical client server architectures, which is the client requests resources from the API, and the resource server responds to those requests. In this case, we have an authorization server in the middle, which is authorizing this access by issuing tokens, which the client holds and presents to the resource server, which verifies them. The main benefit of this is primarily for APIs. They get decoupled from all the complex logic around authenticating the user and authorizing their access. APIs don't have to deal with like passwords, MFA, all that sort of stuff. We can put that behind the authorization server and then centralize access policies within the authorization server as well, and then can kind of scale out the number of APIs and apps we have connected within a single ecosystem. All right, so how does this apply to MCP? Well, it's fairly straightforward. Now instead of an app like Calendly, you have a chatbot like Claude, and that's wanting to access a hypothetical calendar API, which is now MCP server, and Google's authorization server sits in the middle to mediate that. There's been a bit of drama within the MCP specification, which is they introduced a version of OAuth that kind of conflated the authorization server and MCP server, but that's all more or less getting cleaned up. And so we have a typical OAuth architecture that you can apply to MCP. One quick note here is within OAuth, we call these user delegation flows. We call them authorization code flows. Not particularly important to know the name, but the key thing that's important there is that you're acting on an end user's behalf in these flows. So what if we take OAuth and look at all the other things that we need in order to secure agents? There's a bunch of kind of early draft specifications within OAuth or extensions that haven't seen wide adoption outside of these core use cases, but these things apply very well to agent use cases. So let's take a look at what's going on there. The first one is agent-to-agent communication. So what we see with MCP is typically end-user delegation from an application like Claude to MCP servers. What if we want agents to act on their own behalf without any user involved? In this case, we have what's known as client credentials flows that agents can request credentials to other agents or other MCP servers when they're acting alone. So this is quite interesting to look at in those scenarios. This kind of begs the question of what is agent identity in these cases? You've all probably seen this if you've developed an OAuth app. If you're trying to integrate with an API like Google, you typically go and register your application at a developer portal, and you get back a client ID and secret, which then you configure your app with. This works fine for traditional applications, but it creates real issues with LLMs and agents and MCP servers, because what we really want to do is bring tools and agents together dynamically where they don't have prior understanding or prior knowledge of each other and there's no pre-established relationship. So how do we fix that? There is a specification that's been around for quite a while called dynamic client registration, and all this does is let clients or applications register with OAuth servers at runtime. So prior to making an authorization request, they say, hey, I want to register myself, here's my information, and then the authorization server responds with a set of credentials, a client ID and secret in this case, and then the agent goes and talks to the auth server. Now, this is what MCP is currently proposing to use for these scenarios, and there's some kind of deployments of that in practice. I'm a little bit skeptical that this is going to scale in a secure fashion, because what happens here is that it kind of makes all applications or agents anonymous because the initial registration request itself is anonymous. So we have some notion of identity, but there's no real way to authenticate it or authenticate the agent's identity. And there's better alternatives that we should be considering in this case. The first one is for applications that are truly public, like things that are running on your desktop that you don't really care to authenticate. There's a specification called pushed client registration that's out there, which basically establishes a well-known identifier for the client ID, in this case, that green text. There's also capability to include metadata about the agent in that request, and I think this is better than dynamic client registration because it just avoids the whole registration song and dance and the need to store state. The next thing I think we should consider is using URLs and PKI techniques for agent identity. And this is really great when we actually want to authenticate the agents, and in particular when the agents themselves are running on a server side or on the web. So we can reuse the existing identifiers that users are already familiar with and associate with applications by just using the URL itself as the agent identifier. And then we can authenticate those using typical public-private key pairs where the agents sign assertions or HTTP message signatures that then we can authenticate using the public key that's published in a JWKS. And I think this is a really interesting technique. There's a couple proposed specifications called client ID scheme and metadata document that facilitate this happening. Next up is agent attestation. So we've got our agent connected to our resources now, and that agent now turns around and sends all that information up to an LLM in the context window. This seems like something we probably want to be aware of and control. To some extent, we have limited control over this by treating the LLM as just another API. And this works especially for like server-side hosted agents where we control its environment. But it's pretty limited at the edge, like on the desktop or mobile devices where we don't control the agent's environment. So there's a number of interesting working groups where this sort of problem is being discussed. One is called remote attestation procedures in the IETF. It also relates to various supply chain, software supply chain working groups. And with these attestation formats, we can include them in OAuth 2-based authentication and get sort of end-to-end auditability of the agent's environment and the LLM that it's connected to. Next up is transactional authorization. So in traditional OAuth, you've all probably seen this. We're used to controlling access with what's called scopes. And this typically ends up being things like transactions.read, transactions.write, and various things that are more fine-grained than passwords, but still end up being quite coarse-grained for a lot of use cases. So for example, imagine you're trying to do a financial transaction or a commercial transaction where you want to approve like a one-time payment or one-time transfer, potentially with certain amounts associated with it. How would you do that with scopes? Very difficult. So there's proposals in OAuth called rich authorization requests, which basically do things like this, where you describe everything that you're trying to do and you can authorize that specifically. And this is a very promising thing to apply to these types of scenarios. The next up is chain of custody. This is really kind of one of my favorite ones because it shows evolving agent architectures. Within MCP, we've kind of discussed how we secure and authorize the first leg of this, which is the user to the agent and the agent to the MCP server. But that authorization says nothing about what happens further down the back end. And it's a common pattern for MCP servers to talk to other APIs as they sort of wrap them in tools. And for cases where the MCP server and the API are hosted by the same party, so in this case, hypothetical calendar.com, there's OAuth 2 token exchange, which we can use to control the authorization for the back end leg of this that's going over the REST channel. For cases where we are talking to third-party APIs, so there's a third-party MCP server that's stood up in front of a different vendor's API, there's emerging ways to do authorization in this called identity and authorization chaining across domains, which is very interesting and we should all be paying attention to. And then finally, in these cases, we have internal infrastructure. So we have MCP servers talking to other things like Postgres databases on our internal side. This is somewhat beyond the scope of what OAuth controls or has any opinions on, but very important to pay attention to this leg of the communication too. And then this all kind of culminates in complicated agent-to-agent graphs where we have multi-party, multi-actor chains going on here where a user delegates to an agent which then talks to other agents which might end up talking to a resource. And so applying all these various OAuth extensions allows us to have end-to-end visibility and auditability over these channels. Finally, a couple here that are favorites of mine because they talk more about UI and user interaction. So people often think security and ease of use are trade-offs. I strongly disagree with that. Like both by improving UI, you also improve security, and both should be improved together. So one of the things we need to think about is various back-channel authorizations. So your typical OAuth flow, you have a user who's kind of sitting in front of their computer in a web browser, you get their consent, and then you have ongoing access for quite some time. In these new agent environments, this will be much more dynamic. So a use case would be you send an agent off to do your Christmas shopping, and you give it a budget of $100. It goes about and does its work in the background while you walk away. And all of a sudden, the agent might say, well, I found the perfect gift, but it's $110. I need to come back and request access to spend that much money. How do we reach out to the user in this case? They're not in front of their computer anymore. So moving authorization channels more into real-time things like SMS or push notifications, rather than the sort of browser-based flows, is something that's going to be very important. And then finally, multimodal interfaces. This is kind of the frontier of agent interaction, which is what happens when agents just sort of disappear into our environment and we interact with them via voice or video, and how does security and authorization play into those cases. There's a bunch of kind of prior art we could look at within real-time communities like WebRTC and SIP and XMPP that's very fascinating to take a look at. So we've covered a bunch of stuff here. At Keycard, we're building the infrastructure to power this security as you connect your copilots, custom agents, and third-party agents to your app services and infrastructure. And there's a lot here to build, so let's get to it. And just as a pitch, we are hiring if these security and identity protocols interest you. And if they don't, we're also interested in talking to you because we want to help you secure the agents you're building. So the website's keycard.ai, or come up and talk to me here. Thanks. Questions? Any questions? Yeah. One specific thing that we're working on right now? Well, we are basically building like the agent identity piece with the URLs and PKI. Like that's something that's very promising. And then we're having SDKs that wrap all that, so all the complex OAuth machinery just kind of disappears behind a single line of code that you drop into your app. So yeah, we're building the infrastructure there. Yep. Yep. From our product, primarily to like B2B other developers, like people building agents, either for like internal or external use. Yeah. Mm-hmm. Yeah. I mean, I don't think anyone's doing a great job of this right now, to be honest, which is one of the reasons we're working on it. So yeah, I think like the security story of agents, especially like end-to-end, is something that needs to be fixed if we're going to use it safely and securely. So we're trying to make that happen.
How deep have you gone with agent to agent?
Say that again?
How deep have you gone with agent to agent? Is it now 3 layers or 4 layers deep?
I mean, like us as we're like testing stuff, just like 2 layers deep, just to get like one side of delegation. I'm like, this is more for us to like test our security infrastructure. I'm super interested in talking to people like building real agents to see like how they're applying multi-agent hop stuff, because I think that's fascinating. But generally, I think we're pretty early on that, and people are still on like, problem statements that aren't that deep yet, generally. But everyone seems to think it's coming, so. All right, thank you.
Thank you, Jared. And now for our last speaker, coming all the way from Portugal, please welcome Pedro from Neon, now Databricks.
All right, seems good. Hello everyone, my name is Pedro. So yeah, I worked at Neon, as you can see by my both presentation title that I might have not changed yet, and also my t-shirt, but since Friday, I think, I'm working at Databricks, so yeah. To get things started, I went ask the crowd, when you, maybe let's say in the last month or two, has created an app in either, let's say, Lovable, Bolt, Replit, V0, one of those? All right, from these people who has used that app in production or has used that app, let's say, in the week after? All right. So we at Neon have made something to try to fight this. We were tired of just building throwaway apps. We actually wanted to create this sort of implementation reference, and I'm calling it an implementation reference because it is open source, and you guys should definitely check it out after, of how to build an app generation capable of building apps that you can use in production, build good apps with actual servers, database, rollbackable apps, security embedded, and all that stuff. And we, as Neon, also provides databases for like Replit and V0. We also want to learn what's exactly their problems so we can help them further to figure out, yeah, how to really help them. So first things first, I'm going to show like our product that's called app.build. And cool thing is, usually this stuff is on the web. So you would go to your browser and do it there. But something that we have found out, oh, this is, yeah, oh, there you go. Awesome. Something that we have found out is that in the browser, you can do some type of work, but you can't do engineering work. So usually for engineering work, you will be wanting your own setup, your own tools, your own computer. And when you are doing it in a CLI, especially with Node, which isn't the most secure thing ever, but it has access to all your tools inside your computer, so that's also a good thing. So let's start by just creating a new app. And maybe just, yeah, let's do something simple. I want to make sure it works because it's a demo, you guys, you know. To the app, let's see. All right, so it probably asked me something, yeah, like output. Sure, okay. Crude, and just do it. Ask nothing more. All right, so I'm going to go over to the presentation now because this is going to take about maybe 2 to 5 minutes, and then we'll see the result and talk a bit more about it in the end. Oops. Yeah, so this is basically about why did we build app.build. I've talked about it a little bit, so let's keep going. I haven't really presented me properly. I'm Pedro, and I work at Product AI, not at Neon, at Databricks now. Yeah, and that is my Twitter. You can absolutely follow me. App.build, as I just told you, is fully open source. It has 2 repos right now. One is for the agent. Agent, let's say, is where you will see really cool things on how to generate code. It has state machines, it has sandbox, it has deep breadth first search, all kind of algorithms to find out what's the best path on how to generate an app. It's a really cool thing. It's written in Python, and then you have the boring stuff that I worked on, which is the platform, but more on that later. Right, so let's compare app.build and why is it different? Not why is it better, it's really why is it different. So first thing is full open source, which is great. Everyone can take a peek, modify it, do whatever you want. Second thing is that it is full stack, so it has a real server, it has a real DB, it is free, which is nice, you can use it. We have no billing, so take advantage. And then there is the other thing, which is really great, it is equipped with tests. So every app that we generate have both backend tests, integration tests against the real DB, run in sandboxes, and they also have a playwright end-to-end test. So every app that you'll generate will have not as many bugs as, I guess, the other ones. Is it good for non-technical people? Absolutely not. It uses a lot of words like, yeah, it uses a CLI, so it's obviously not good for non-technical people. Yeah, it's a choice we made. The other different thing is the UI. It is a CLI right now. We plan to do a web base, of course, but for now we figure out that CLI is really good for technical people, sorry. So I guess engineers and software developers and all that stuff, because they can just do it, I guess, in their own computer. Passing a little bit for the architecture of app.build, it is kind of simple. It only has 3 parts. And you can run all of these parts in your computer. So yeah, you can test it after. The first one is the agent. This is just a stateless service. It literally just outputs code. It does nothing more. It just outputs code. And then some stuff like maybe commit messages, app names, and some other metadata. But that's not really interesting. So that's the code part. That's good. On the platform, we have all the integration on how to make this happen on the cloud. That is fully GitHub integration. So every generation has a commit associated to your account. Every commit has a deployment. So it's like rollback, natively rollbackable. And it also handles the authentication through the CLI, which is the entry point here. So other thing we did is all the stack that we chose, people has told that it's kind of weird. Like, what the hell is gRPC? Maybe someone is asking. And why did we use like Drizzle? Why did we use like Bun? All that stuff. And reason being, we chose a stack that we know would work well for generating code. So for the ones that don't know, Neon is great with their branching capabilities. You can roll back in time. So any migrations, it's just there. It's instantaneous. Yeah, it's great. gRPC enforces TypeScript safety, so backend and frontend are always in sync, so that's always great. Zod, Drizzle, that's just better for managing database, in our opinion, plus some other weird stuff in the agent that I can talk about after. And yeah, Bun, I don't know, we just like Bun. On the front-end part, we didn't want something like Next or, I don't know, we didn't want SSR at all. We wanted to make something a bit simpler, a simple SPA that communicates through HTTP. So we just went with what works, and that would be Vite, React, gRPC again, and then to make things beautiful, Radix, Tailwind, and Playwright for the end-to-end test. So now answering the question that we did at the beginning, like why did we build it? One, because we have opinions, and I guess opinions different from what was already made, because we didn't see anyone doing things the way we did. And we want to take that into our hands and see if things actually work. We are still not sure. This is like a baby that we have refactored like 3 or 4 times already, and we just launched. And we already have ideas to refactor another time, at least. And the other thing, like we discussed at the beginning, is we want to go beyond throwaway apps. And so this is like building a CLI was a crazy idea, but I guess it allows us to do more engineering work because we are already on our computer. So the ejecting experience from going from the web to our computer is like much faster. All the servers that we built are long-lived servers and not serverless crap, where you cannot do like cron jobs and stuff like that, at least not natively. Security-wise, it's also, I guess, a little better because it just uses imperative security on the server, not like errorless rules that agents can absolutely not create, and where your apps will be hacked in like 2 weeks, like we have seen all on Twitter. And yeah, database, it has backed by Neon. It's absolutely great for agent work. We have seen it countless times in countless customers. Yeah, we know that it just works. That is the QR code for app.build website, where you can find like a blog post on how is the agent built and a lot more information on it. Now let's just go back here and see what it did. All right. OK, let's start here. So every app, as I told you, has a GitHub integration, and every deployment is a commit. So we can, I guess, just look at the commit. This is the initial, and I guess implement crude. Yeah, we can look at the code. It's all very beautiful, of course. And yeah, as I told you, it has tests. So these tests are also passing, else we would go into an error from the agent where it would just tell us it wasn't able to generate. Right, so let's see what else we got here. Yeah, so we got a URL to which our application was deployed. All right, so it's still under construction. It might be under construction for a while, so yeah. Anyway, I can show you another app. There you go. It's writing. So I have like my assistant, which is looking at the logs live there, and it just tells me that, thank you, Mario. That's appreciated. Oh, there you go. Nice. So let's see if this stuff works. 1, 2, 3. OK, nice. Kind of works. Let's open it in. OK, so there is a real database there. And yeah, it kind of works. I'm surprised. Yeah, so if we wanted, it could simply like just do a simple iteration now and tell it like dark mode or something like that. But yeah, it might take a while. Anyway, that's what I wanted to show you guys today. You should definitely check out our repos, mainly agent. I think it's like really amazing the way that our team has architectured this to, I don't know, like I've never seen an agent whose base is a state machine that is running on code sandboxes, that is yeah, iterating in ways that it's really mind-blowing. I'm not sure if it's good, but it looks like so. Yeah, I want to appreciate everyone. This was a really chill talk. Let's keep pushing and let's keep doing open source. Thank you. Yeah, if you have any questions, please feel free to make them. Yeah, go ahead.
First of all, great talk. Thank you very much.
Thank you.
Just curious, why not just run a fork for
Yeah, that's a great question. That's not where we wanted to go. We really wanted to invent something new. Yeah, just to say something else, this is what really was some academia things that we are trying to do here. It's not as much to make money per se, also that would help, but we don't even have a billing system. We really wanted to understand what problems were app builders facing, so like Neon could actually, I don't know, get more customers and help our existing customers to make better products. Yeah. Yeah, please. Yeah, so the way that the core is built is it is, let's say, so we can only make right now full stack applications that are React with Node, right? But someone asked us, can we build Python Streamlit or whatever, I don't know, some Python stuff. And one of our engineers just said, sure. He changed 2 files, and boom, he was generating Python applications. The way our agent is built is completely agnostic, and we just need to change what we call playbooks. So it's just the prompts where we say, like, basically the rules. And yeah, we can literally generate whatever. So to answer your question now, yes, we are going to incorporate this probably, maybe that's our plan, into Databricks, and maybe, who knows, generate actual Python-based apps with this very same agent score, and that will still be useful and will be around in a while. Awesome, thank you.